SwayamPrabha. Digital India. Educated India.
So after discussing about nucleation in the liquid and the solid, we are going to start the subject of solidification. But I have already discussed nucleation part of the solidification. So therefore the things which needs to be discussed is basically how a solid nuclei in a liquid grows and form the complete solid. But before I do that, it is better that I tell you why solidification is so important and the aspects which you need to consider while dealing with solidification as a phase transformation. So as you know, casting is normally synonymous with solidification, and major industries in the world, they produce different kinds of castings, industrially as well as even small scale. So when a casting is made, liquid metal is poured into a mold. The picture here shows the same thing. There is a mold made of sand and a cavity is made inside the mold for the object whose shape has to be made by the solid. So therefore, to pour the liquid metal, it can be pure metal, it can be alloy. Normally it is an alloy. We need to have a system through which the metal will be poured and transported to the cavity. So as you see here, this is the cavity and this is the pouring cup, and the metal actually poured here slowly travels to this and reaches the cavity. As most of the materials in the metallic materials shrink during solidification because of a change of density, so we need to take care of that. That is done by a riser, using a riser which will allow us to keep hot metal as an extra source. If at all there is a shrinkage in the casting, that can be taken care of by this riser. Well, I do not want to give a complete lecture on how the castings are made, that is a different course altogether. But let me tell you the basic important aspects. The liquid which is poured in the pouring cup travels to the cavity and then starts solidifying. And because of sand mold, so therefore walls of sand actually acts as heterogeneous nucleation sites. And once the nucleation happens on the surface or the walls of these mold in which sands are present, the solid grows into the liquid. So our objective of phase transformation in solidification is basically to understand how the nucleation happens, and the growth followed by it can be whether understood or not. So nucleation is mostly heterogeneous type, that I mentioned in the last lecture. So therefore all the theories which I have discussed in the last lecture can be used to explain the nucleation aspects of that. So this is basically known as a gravity or sand mold casting, which is predominantly used in the industries to make different objects, but that is not all. Well, this is basically after the casting is made. You see, this is the casting, there is a hole in the casting, this is what is the core, and these are the riser and the pouring cup. So after the casting is made, these two pieces are cut off by using some oxyacetylene flame, and the casting is separated. Now there are many techniques in which solidification is used extensively. One such is basically known as continuous casting. This is used extensively in steel and aluminum industry, in which we pour liquid metal in a ladle. Ladle is a reservoir, and from the ladle liquid metal is from the ladle liquid metal is poured in a tan dish. Tan dish is a reservoir, not a ladle. So ladle actually used to transport the liquid metal from steel melting shop or aluminum melting hot metal cells, and then this is poured into a tan dish. Tan dish keeps the liquid metal in a steady state conditions. From the tan dish, it's poured into a mold, open mold. Basically it's a water cooled copper open mold, And as the basic picture is shown here, as the liquid metal is poured into the water cooled copper mold, a thin layer is solidified or skin solidified at the interface, and inside still remains in hot liquid conditions. So therefore again the nucleation happens at the interface between this solid copper mold and the liquid, and this is again heterogeneous type nucleation. So as this is basically a chilled zone in which the liquid metal has been solidified very rapidly because it's copper and also water cooled, so the heat transport is very high. So number of nucleation, number of sites on the places on which the nucleation can happen is also very large. Not only that, because it's a rapid process, cooling process, therefore the sizes of these grains which may form along this interface is very small. Subsequently, as the liquid metal, as these piece, the liquid metal piece flows by the conveyor belt, water is sprayed onto the surface so that heat can be extracted and everything is solidified at the end. So this is a mass scale production process in which solidification is extensively used. So therefore it is important that to understand how actually heat transport and solidification happens in such a situation. Well, not only that, there are welding techniques in which solidification is taking place every time a weld is made. So as you see here, there is a welding of basically arc welding in which a electrical arc is used to join two pieces of metal. Basically it's nothing but an tungsten electrode. Normally it can be actually used to generate only the heat, and then sometimes we also use a feeder or feeding electrode which will melt and allow us to join the two metals. Here you see there are actually two pieces of metal getting joined together and using arc flame. So in this situations only liquid, small amount of liquid is generated between the two pieces of the metal, and because of that the liquid is contact with the two pieces of the metal, therefore there is an empty number of heterogeneous nucleation sites present on the both surfaces. So solidification is actually starts with the heterogeneous nucleation of these grains. The important aspect is this, how the grains then grow, because this welding torch moves at a certain velocity during welding process. As you have probably seen many of these welders when they do welding of the pipes or some other objects in the different places. So therefore the basic purpose, aspects which is more important is the growth, how the growth of the solid happens in the liquid. This is a gas welding which is also used. We can use oxyacetylene film to create a heat source. As you see here, this is basically a one pipe here, this is another pipe, they are getting joined, and using a filler rod. This is a filler rod. Filler rod is nothing but again a metal alloy which will allow us to make a nice joint. So the schematic picture shows on the right side that there is two pieces of the metal to be welded, and filler rod is placed like this, and the flame which is placed at the intersection of these filler rod and the two metal pieces melts down both these three things, actually two pieces of the metal as well as the filler rod, and creates a liquid pool, and this liquid then solidifies. Again, because two pieces are solid, because welding is happening only small region, so bulk of these pieces remain solid, therefore there is empty number of heterogeneous nucleation sites present on the surface. So only issue is here how the nucleating solids grow into the liquid. So that's the basic aspects. One can use laser also instead of a arc or a gas welding torch. One can use a laser. Laser is a clean source of heat, so therefore it can be actually focused on a certain spot also, unlike the other two cases. Here it shows that how things happens. You have two pieces of the metal, and as the laser actually falls on in between the two pieces, it melts both the pieces. Because of that, there is a weld pool or liquid pool generated, and as the laser moves, or basically the sample moves, laser remains stationary, the position of the laser beam on the surface also moves. Because of that, the pool gets solidified at a certain rate. So that's why the growth of these things, those of these nucleating phase which are forming at the two joining surfaces, is the most important aspects. So all these industrial aspects, this is shown here again all the industrially important processes requires you to understand the solidification. You see here, this is basically different zones of the welded. This is the fusion zone in which you form certain geometrically important features known as dendrites. Okay, those we will discuss later on. Dendrite is a T-like structure, and this is forms at the interface between the solid metal and the liquid, and then it grows inside the liquid. So the basic aspect is that how these dendrites, which is shown in a bigger picture here, you see here, these are the dendrites of superalloy, nickel-based superalloy going into the melt. How these actually grow into the liquid, that's the question we need to understand more. Okay, nowadays people actually all talking about metallic foams. Foams are actually very important industrially because foams are used in the as a shock absorber in the cars or even the defense applications where you need a ballistic things to protect ballistic armor basically to protect from the bullets. So foams are actually also made from liquid. Basically the foams are made from, this is shown aluminum as a foam. You can actually have aluminum melt with a little bit of calcium, and then calcium actually stabilizes the foam. Basically foam is nothing but when you take a put soap into a bucket and then started stirring it, you will generate foam. But something else which stabilizes these foams. Metal is a little bit difficult than a common example I gave you. So what happened actually, calcium actually stabilizes the foam surfaces. So once it is heated up to 600 degrees Celsius temperature, this is known as thickening. Thickening means it makes the liquid viscous. That's how actually these foams get stabilized. Then we add little bit amount of titanium hydride, TiH2. So what happens, titanium hydride into liquid aluminum reacts and hydrogen gas is produced. This hydrogen gas creates a bubble, and these bubbles are nothing but foams. And because it's a viscous liquid and calcium is present, so therefore the foam walls are basically get stabilized because of this calcium present in the liquid. So once this gets completely bubbled up, just like a bucket you put water and then soap and then stir, it will be full with foams. Then you can simply cool it down to solidify it. That's how the foams actually form. And then you can cut and use it. So foams are very important, but basic thing what I am talking about you is that again here the solidification is very important. Remember, nucleation of these bubbles is not a big problem because hydrogen is basically bubbling up, or because hydrogen has a certain amount of hydrogen can get inside the liquid metal, rest cannot. So once you put more amount of hydrogen, it will create bubbles, it will try to come out, and in the process it creates more bubble, and these bubbles actually grow. So therefore it's a growth of that liquid into a bubble form. That's what is the important aspects in the foam formation. So these are all industrially important processes. Another important industrial process which nowadays is very coming up is known as what is known as additive manufacturing or rapid laser manufacturing. If you want to produce an object and to see whether it's possible to have a particular shape and it has market need or not, normally rapid prototyping is used. So rapid prototyping is just a routine technique nowadays for any objects, whether you are wearing a shoe or wearing a goggles or what, it's rapidly prototype first and sent to the market, and then based on the market feedback mass scale production is done. So in that case this is actually used nowadays for metals. We use laser as a layer structure. You can see here the laser beam has been used to produce such a kind of structure in which everything is produced layer wise, and this is again done using solidification because we use powder as a source, melt it down and then produce these layer structures. So thus rapid prototyping of metals actually are using solidification as a tool to create different kinds of structures. So these are all examples where I have shown you how solidification is so important in the day-to-day life, because we need to produce different objects for our need. So therefore solidification must be used, and this is probably one of the cheapest technique in which liquid metal can be given any shape. So thus it is important as a part of course of phase transformation that you understand what actually happens atomistically. Atomistic mechanism of growth is what is important, because atomistic mechanism of nucleation I have already discussed with you. When you talk about atomistic mechanism of growth, you have to understand growth means what? Growth means basically growth of the stable nucleus, which is already formed in a liquid, and that growth happens because of the attachment of the atoms from the liquid to solid. The atoms in the liquid, they jump across the interface and join the solid and become part of the solid. That's how the growth happens basically. In a very rudimentary way, we can say that, but it's not so simple. That's what is the basic purpose of discussing today in the lecture. So any solidification processes is obviously categorized into two steps, nucleation and growth. Once the nucleation forms, the growth is nothing but bigger, making the nuclei bigger in size. So how we can make it bigger? By simply attaching more atoms to it. So therefore atomic attachment kinetics becomes the most important aspects in the solidification or in the growth process during solidification. And this atomic attachment actually depends on the type of surface we have, type of interface basically we have between the solid and liquid, obviously, because atoms will jump from the liquid because of the thermal vibration, and then they will join the solid surface. Therefore the interface between the solid and liquid will dictate what kind of process will happen. Anyway, there are two types of interfaces normally present in a solid liquid solid actually. One is known as atomically smooth. This is directly taken from, these pictures are directly taken from the Porter and Sterling book. You can read it if you have the book, otherwise you can actually available on different internet sites also. So there are two types of surfaces created. One is known as atomically smooth, okay, what is known as A, other one is atomically rough. These are very confusing terms for the students. Okay, atomically smooth means it's smooth. What do you mean by smooth? With smooth we mean that it's a very nice surface, and rough means we assume it's basically a lot of jagged things are there. Okay, so as you see here, basically in a atomically smooth surface, okay, atomically smooth surface is A, and actually P and C are actually atomically rough and atomic diffuse interface. So let us first discuss about the B, which is basically a diffuse or atomically rough surface. So as you see here that in atomically rough surface you have a diffuse interface. What is the meaning of diffuse interface? That means there is a large number of atoms are present at the interface. These atoms are neither part of the solid nor part of the liquid. Why? Because in the solids atoms are nicely ordered. In the liquids atoms are random. There is no order in it. Okay, and in between atoms are actually somewhere they are ordered here, somewhere they are rough, somewhere they are not ordered. So that means that they are neither completely part of the solid nor completely part of the liquids. When you have such a kind of interface, you can clearly see if there is an atom in the liquid, bulk of the liquid, and the atom needs to come and jump and join the solid. What it can do, it can basically come and sit over here nicely, or it can easily come and sit over there nicely, or it can easily come and sit over there nicely, and then satisfy its bonds. 1, 2, 3 bonds can be satisfied, right? Then slowly this atom can migrate, because it is in very high temperature, because the surface is in contact with the liquid, the diffusion is very fast, diffusion coefficients are very large here. So this can easily migrate and reach these places. Even if it is, while it is travelling, it can easily occupy these positions nicely and find these all bonds can be satisfied. So therefore in a atomically rough surfaces or diffuse interface, there are large number of places where the atom can easily jump and sit and become part of the solid. But that's normally happens for the metals. Most of the metals, silicon dioxide, titanium dioxides, okay, type of things in ceramics. But there are other things like silicon, germanium, metalloids, where the surface is not actually like that. Surface is basically what is known as jagged. So what is the meaning of that? If you carefully look at, the surface is basically faceted. Okay, it's like this. It's no longer rough enough, but it's faceted. Okay, when a faceted surfaces, obviously atoms cannot go and sit on every positions, because if atom sits here, suppose it sits here, it is only satisfying only one bond, rest of the bond are remaining dangling. So therefore energetically that is not favorable. On the other hand, if the atom actually goes here in these deep wells, they can satisfy many bonds, because they can satisfy bond this way, they can satisfy bond this way, this way. So therefore, in this kind of interfaces, atoms has to go to a particular place to sit it nicely to become part of the solid. That is why all the jumps atoms will make from the liquid will not be successful one to become part of the solid. Some of the jumps will be successful, some of the jumps will be unsuccessful. That means some jumps atoms will basically come from the liquid, join the solid, and it can go back if it is not able to recover its energy completely. Well, that's the basically way things happens, but let us do it in the board with a little bit of analysis how things happens actually. I will assume a simple potential barrier, okay, from a solid to liquid. So let me just draw. Let us not consider those interfaces right now. Simply you consider a situation where you are dealing with, this is a distance axis and this is free energy G. And suppose this is my solid, this is my liquid, and this is the interface, right? This is the interface. Remember, atoms in the solids actually in order manner, therefore most of the bonds are satisfied. So therefore the potential of the atom, basically potential means is its energy of the atom basically low compared to the liquid. In the liquid, atoms are moving haphazard, so bonds are not satisfied. So therefore in a solid, if I mark this as solid, this is as a liquid, solid will have always lower energy than the liquid, okay, always, because solid atoms are ordered and they are bonded. But at the interface energy will be high. Why? Because at the interface atoms are undergoing a jump basically, that is why. That is the main reason they will have more energy at the interface. Now this difference between the solid and the liquid is what I can define as a delta G solid to liquid. This is the energy gain when the atoms actually jump from the liquid to the solid. And this energy, which is shown as a peak from here to the liquid, is basically known as, termed as delta G star transport T. Okay. So what does it mean? This means that this is just like a gain boundary migration or basically atom moving from one place, diffusion actually, one place to other. Basically this solidification also can be considered as an atomic migration from the liquid to solid. So therefore it's a diffusion, one kind of diffusion, but it's not only diffusion but also something else. So that means this is an activation, activation control process. When you have activation control process, if this is activation control process, then what is the rate? Rate of the process is basically can be easily defined as the frequency of the atomic jump from the liquid to the solid. Let us suppose this is mu L multiplied by multiplied by e to the power delta G star by kT, where delta G star is basically the transport barrier or the barrier height in per atom divided by the thermal energy per atom, that is kT. So this is what is basically will give you the rate, because this is related to the frequency of jump, it makes jumps, and this is the probability that they can cross the barrier. So all atoms may not have sufficient energy to cross this height, okay. Some of atoms will have, some atoms will not have. Once it's crossed this barrier, basically the atom slide down, or basically atoms basically slide down along the energy energy gradient and become part of the solid. That's what happens when you have a solid. So in the solid actually atoms are nicely ordered manner, but in the liquid they are not, they are haphazard. In the liquid they are haphazard. Okay. So that's how actually things can happen. Now using this concept, two different types of interfaces, let me explain. So I can actually then do a flux calculations from the liquid to the solid, and explain you how the flux can be calculated. Obviously, as I told you that when you are talking about the net growth means net atoms getting attached from the liquid to solid, we need to consider both the jumps from the liquid to solid, which is known as a forward jump, and also backward jump from the solid to the liquid. Because some atoms, as I said you clearly, may jump, come to the solid, but may not feel energy has been reduced because of the type of interfaces we have, and then go back. That's always possible, because if they are not sitting at a very nice positions where most of its bonds are satisfied in the solid, it can go back. So therefore we need to consider both the flux from the liquid to the solid and flux from the solid to the liquid, both. So what is the flux depends on? Obviously flux will depends on total number of atoms. Yes, if liquid has NL number of atoms, they all can jump multiplied by the frequency, okay, and then obviously the factor which comes is that not all the jumps will be successful. So therefore that it will jump and it can come back, because some of the atoms may not be able to cross even this barrier, they will go back to the liquid. That's possible. So there are two types of things. One is that atom jumps, cross the barrier, is a solid, do not feel comfortable, go back. That's what a reverse jump. Second one is that atoms try to jump but may not be able to cross this barrier. So fraction of liquid atoms of NL multiplied by this frequency into exponential minus delta GT star divided by KT is what is this flux in the forward direction, that is from the liquid to solid. The solid to liquid, obviously NL will be defined, NL will be substituted by NS, number of atoms, okay. Again the frequency, you can write down frequency as solid also, but does not matter because frequencies now of the vibrations remains almost same. And then not all atoms may not be able to go back, because if they have to go back they have to again cross the barrier. So that fraction has to be multiplied, but this will be different, exponential, because the barriers now is this plus this together. So we have to write down delta G solid minus solid to liquid plus delta G star T divided by KT. Everything here is per atom basis, therefore there is no need of dividing by that. Now I can actually do a flux balance calculation. Flux balance calculation tells you liquid minus solid, solid minus solid to liquid. As you clearly see, I can take common of mu L exponential minus delta G T star divided by KT. I can take the common this factor, and I can write down this as NL mu L nu L. So NL nu L is, what is that I have taken? This cannot be taken out, right? Yeah. So only factor I can take out this. So NL VL FL minus NS. Oh sorry, VL can be taken out. Yes, mu L can be taken out. It's a common, and F alpha. This will be exponential minus delta G solid to liquid by KT. That's basically is my my net flux, and that's nothing but the growth rate. Okay, so that's nothing but B. For any kind of interface you can talk about it. So you can clearly see it's basically has a P exponential term that depends on the frequency of the vibrations, that depends on the barrier height, this barrier height for the jump, and then it depends on something else, depends on these number of sites available, how many of the jumps are successful on the liquid to solid, similarly for the solid to liquid, and also on the solid to liquid sides we have a exponential term related to this part, that is the difference of energies between solid and liquid. Well, we will keep this equation intact and discuss further, okay, because it requires some more discussions, we will do that.